next speaker, that would be JanDidden.
That's me.
Probably knows more people in audio than anyone else I know because he would interview them for Audio Express magazine and Elector. I guess maybe you're thinking about what you could do with all that.
Well, the next one is to be interviewed with you.
Yeah. And so he decided to put out a magazine, which, you know, in these days, that's really an intelligent thing to do, right? Put out a paper-based magazine or something. But it turns out he says it's going to be a book zine. So I said, oh, maybe. And he's got 4 issues of this.
5.
Right? 5 issues out. And if you're into DIY audio and you have some technical interest in it, he's got projects in here, and you can just make the project, or you can learn a hell of a lot about it. And I mean, he's got everyone who's anyone contributing to this. So I mean, we got Cordell in this one. We got Linkwitz.
Mr. Nelson Paas.
We got Nelson Paas. I mean, Stuart Gallagher. I mean, we got people who really know their stuff. So I recommend you buy these. These are about $20 a piece, and you can find them on his website. But they're just like treasure chests for those of us who care. But today, he's going to talk about what does feedback really do, because I can read.
Yeah.
That's how I know that. So good luck on that.
Yeah, thank you. Yeah.
Jan, please.
The title suggests that I do know what it really does, but that's not really true. But I'm trying to find out, and I want to share a few things with you. The idea from this came when the people from Elector, who are now running Audio Express, they asked me to do a workshop on feedback. They would tape it on a DVD and then sell it, of course. And it ran to 2.5 hours. But then they came back and they say, we call it a master class. Well, that really embarrassed me because it's just a workshop. But some of the slides and some of the stuff out of that, about 20 minutes I took and decided to share with you. There's actually one slide with equations, but don't be afraid. What I'm trying to do is to talk about how things hang together and to give you some kind of an insight. I will briefly talk about 4 things. Bandwidth extension, how does that happen as a result of feedback? What is the difference between phase shift and delay? Because a lot of people say, well, feedback comes after the fact, it's delayed, so how can you fix something after it has happened? Something about the effects of clipping, and what Nelson also briefly mentioned, if you have distortion in your amplifier and the distortion and the feedback takes the distortion back to the input, you would expect to get distortion from distortion, which gets a big mess. The story is a little bit more subtle than that, and I have 2 slides for that as well. You have the next slide? I have to give credit for this idea to Bruno Putzais, who is somewhere sitting there. I took your idea, Bruno, and I worked it out a little bit. I hope you don't mind. Just to show how I think about hi-fi reproduction in your living room. Suppose you like art, you like the David from Michelangelo, and you want to have it in your living room. Well, you don't normally have the amount of money to buy the David because it's somewhere in the museum, very expensive. So you want a reproduction. Well, what kind of reproduction do you want? Well, you can get a mold of the original one, which would be this one. Or you can say, well, I get an interpretation of the David as is done by Mr. Donatello in bronze, which looks different, but for him it's David. And there's another guy, Verraccio, who made yet another interpretation of David, where he shows the head of Goliath that David cut off after he killed him. So any of these will do as a reproduction of David in your living room, and it's up to your taste and what you want, what appeals to you. And it's a similar thing with hi-fi and with audio. Some people like Class A or Tube or Solid State. They have all their own character, and there is no good way of reproducing. It's what you want, and we should not be religious about this is good and this is bad. It's different. By the way, this thing, this one is in the British Museum. This fig leaf hangs a little bit in the back, and when Her Majesty the Queen comes to visit, the fig leaf is hung there. True story. Next slide, please. Okay, this is the one slide with the equation. A amplifier, and this could be a very complex amplifier, or it could be a relatively simple amplifier like Nelson's, or it could be an op-amp or anything. I just draw it this way to be able to talk about feedback and not talk about what's in the amplifier, because that, to a certain extent, we won't talk about it right now. So, very simple, your input signal, your output signal, a fraction of your output signal gets fed back to the input, and if you do the math, you find out that your closed loop gain, so the gain from VI to VO with this feedback, is this formula. And this formula shows the open loop gain of this amplifier, and it shows something we call beta, which is the fraction of the output that gets turned back. What is the great thing since sliced bread from feedback? Well, if your open loop gain is very high, and beta is normally 20 or 30, depending on the gain of your amplifier, mathematicians say you can forget about this one, because this one doesn't matter if this is 100,000 and 5,000. We can leave out the one. But then again, the mathematician says if we do that, we can also divide here and here by A0. And what remains is beta. And that's the thing that people associate with feedback. If your open loop gain is large enough and you do the approximations, the amplification of this amplifier from input to output depends only on beta, which is the resistive divider. So at one swoop, we've gotten rid of all the distortion, all the limitations, all the bad things of this amplifier. And of course, it doesn't work like that. And that's the 3 or 4 things that I just want to mention, why it doesn't always work like that and what are the hidden things behind it. Next slide, please. Okay. For instance, we know that if you have a feedback amplifier, that the bandwidth is larger than the amplifier without feedback. How does it come? How does it work? Well, if this is your amplifier without feedback, at a certain point it starts to roll off. So this is your bandwidth without feedback. Now, this amplifier itself, there's no change. Whatever we do on the outside, this amplifier will not change. It will always work open loop. So there's always a little input voltage that you need to get the output voltage. When the frequency increases and the gain starts to roll off, that means that there's less going back here, because the gain starts to roll off. It also means that this gets larger, because this stays the same, this gets lower, so this gets larger. So what you see, if you put your scope on the input of the amplifier, and you increase the frequency, you will see that the effective input voltage goes up. And of course, the fact that the effective input voltage goes up works against the falling off of the gain of the amplifier itself. Do I make a little bit sense? That's how bandwidth extension works. Can we get the next slide? So the effect, what you see is, I draw it here also for on the bottom side, but it's conceptually the same. If your amplifier without feedback starts to roll off, and that effective input to that amplifier starts to rise to counter that effect, you see this later. You see that at a certain point, of course, the gain here is so far down there, it doesn't work anymore. But you see that it hangs on a little bit longer before it starts to fall. And that's your bandwidth extension. So feedback is nothing magical. It just works because the output of the amplifier drops. That means that the input signal rises, and that helps to maintain some of the gain until it falls off. And these are simple things that, for me, really give me insight of how feedback amplifiers work. How it is that all of a sudden the bandwidth is more than it was before. Next slide, please. you can look at that on the scope. Let's take a hypothetical case where you have a square wave going into an amplifier, and we have no feedback, and the amplifier has a limited bandwidth, so the square wave comes out like this. Now, we know that if you put feedback around the amplifier, that we get bigger bandwidth, so we expect, with feedback, we expect this to improve. Next slide, please. That's what it does. So if you do feedback, we get a better reproduction of the square wave. But remember what I said, that the cost that you pay for that is that you need more effective input voltage in the amplifier. And we see that on the next slide very, very nicely. This part is more or less filled in by the feedback. These are the high frequencies, of course, in the transient. And if you look at the effective input signal, the plus and minus input of the amplifier, you will see this. The fact that you feed back the signal causes the input signal for the high frequencies to get up, so that in the end, the square wave looks pretty much like the input, or better than the input square wave. So that's exactly what we've been talking about. Next slide, please. And of course, can you go back? Can you go back? And of course, if you overdo it, if you get too much feedback, then this very high effective input signal may overdrive your input stage, and that can lead to all kinds of troubles. But that's something for another time. Next slide, please. Okay. Phase shift or delay. This is something that I've done a lot of discussions online. You have an output signal that is shifted in phase, and you feed it back, and how can you now correct something that has already happened? And if you look at the input and output, you see a sine wave, and then you see another sine wave that's phase shifted, and you say, see, it's clearly delayed. Well, it's not delayed, it's phase shifted, and it's not the same. Let's just think of an amplifier as, all amplifiers are filters, so let's just think of an amplifier as something with gain and a first order RC, because the bandwidth is limited at higher frequencies. The gain drops down, and we can simulate it by an RC. Now, the next slide, I put on the input, I put a square wave. And what I see here on the capacitor, I have to be more disciplined with this thing. What you see on the capacitor is this red triangle. Because when the square wave goes up, current goes in here, starts to charge the capacitor in a linear fashion, or almost linear, depending on the RC values, of course. And then here, the square wave drops down, and this goes down. So the takeaway from this is that immediately when the square wave input changes, the output changes. So there is no delay between input and output. If he goes down, this starts to go down. Of course, delayed, because the capacitor has to be discharged, but there is no delay. There's lots of phase shift, and that is why the high frequencies here are shifted in such a way that at the end you get this wave. In fact, mathematicians would call it an integrator. You integrate this voltage in the capacitor. But there's no delay in the sense that anytime there's a change here, there is immediately a change there. And that is important. So that allows the feedback that there is really no delay in the feedback. There's a phase shift, but there's no delay. So at any time the input signal of the amplifier changes, at that same moment the output signal of the amplifier changes, and at that same moment the feedback signal to the negative input changes. Well, there is a delay of a few fractions of a microsecond, but not what we normally would think. Now, so this red wave, is the integrated input signal. Now, if you look at the next slide, we do the same thing, but with a sine wave. We put up a sine wave, and we look at the capacitor output, which is another sine wave. Why? Because the integrator the integration of a sine wave is another sine wave. But it's in phase shifted. And so here you see clearly the phase shift. But you should not make the mistake and say the output is delayed by this. The envelope, the shape of the output is delayed, but anytime something changes here, something changes here. If it goes from rising to falling, it goes from convex to concave. So any change in the input is immediately reflected in a change in the output. So even if you think there is a delay between the two, it's not really true. It just looks that way because an integrated sine wave is another sine wave. Does that make sense? So if people tell you feedback cannot work because there is a clearly delay from input to output, no, it's not a delay, it's phase shift. And it doesn't prevent the feedback to work. Anyway, it's stupid to say feedback doesn't work because we have amplifiers in our room that work with feedback. So. Okay, next slide. The badness of clipping. Again, it's often instructive to look at the waves of the input and the output of the amplifier. If I have an input signal here, that middle one, and I have an output signal that gets to the point where the power supply is, it can go up. So the output of the amplifier is limited, that lags below the input signal, because the output cannot rise. Same on the negative side. Now, the difference between the input signal here and the fraction of the output signal determines that effective input signal on the amplifier. You remember, you had an input signal on the amplifier and you had a fraction of the output that gets fed back. Now, the output cannot go higher, stays behind, so the fraction that gets fed back also stays behind, which means that the effective input signal for the amplifier rises. And you see that here. If you see the effective input signal to the amplifier, it's a nice sine wave as long as you're not clipped. But when you're clipping, then you're going to miss a part here. And oops, you see that the input signal to the amplifier itself, the difference between the plus and the minus input, rises. And this can, of course, cause overdrive in the input stage. It can cause overdrive that hangs on and takes some time to recover if your amplifier is not designed well. So that is the cause from the fact that clipping in an amplifier with feedback can be very hard, because as a result of the feedback, your input keeps on trying to rise to keep the output at a certain level. So you really overdrive the amplifier here, and you get very, very hard clipping. You try to get the last millivolt out of that power supply voltage. Putting your scope on the effective input between the plus and the minus gives you a lot of information on this. Okay, next slide. Okay, the last thing I want to mention is also something that gets discussed a lot online. If you have an amplifier that has feedback and it distorts, then the feedback takes your distortion and puts it in the input again, so you get the distortion of the distortion, etc., all in a merry-go-round. The story behind that is that I think it was Baxandal who did a test in the 70s with a single JFET stage. He built a single JFET stage amplifier with 0 feedback, which is here, and you looked at the harmonic distortion. You know, it's 25 dB, minus 25 dB second, blah, 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 minus 55 third, etc. And then he started to increase the feedback around the stage. And to his horror, he saw that when he increased feedback, all of a sudden, the higher harmonics start to rise instead of to fall. And even some harmonics, like the 6 and the 7, which weren't there before, with 5 or 10 dB of feedback, all of a sudden you have harmonics that you didn't see before. And that's the background between the story of feedback causes distortion of distortion. But don't forget, this was only with a single JFET stage, a very, very crooked transfer function, quadratic transfer function, And if you go to the next slide, if you have an amplifier that's reasonably linear, like a class A, B output stage, you don't see that. You see that at 0 dB feedback, you have a certain range of harmonics, and then if you increase feedback, all your harmonics drop. And there's no new that come up. There are some wiggles here. I don't know where they are from. Maybe they're from measurement. I don't know. Both this picture and the previous one are from the book from Bob Cordell, Designing Power Amplifiers. There's a lot of information behind that, but I think those two pictures are very much are very clear, and they show that if you have a reasonable linear amplifier to begin with, you don't have any fear of causing harmonics, off harmonics, off harmonics. Okay, I think that was it. That was it. Thanks, that was my little thing.